Yeah, so my name's Adam Timler. I'm the founder of a company called Turing Meta, which is a consultancy that specializes in using biological research to help us to solve organizational problems. So as a as that requires a bit of explanation, this talk is an attempt to explain why I'll be using the science of biology to look at organizational problems in human organizations, as opposed to any of the other sciences that you could look at, for solving the same kind of problems. So yeah, this is a quote about. I was looking for a quote by Einstein about the great dragon and grabbing the tail of the dragon, and that quote doesn't seem to exist, but this quote does exist. And it's about this. I like this idea of a dragon as something you can't see in its entirety. You can only see pieces of it, and that's what this quote is about. Obviously, in reference to quantum mechanics. So uh, um, so yeah, so this is what the talk's about. Um, and so to start off with, this idea of something you can't see in its entirety this is why the problem of not being able to measure something that you can't see in its entirety is the idea that the organization can be like this dragon. So as an example, obviously if your company is very small, you don't really have this problem, but people who are in a company that is larger than say 150 people, um, to experience directly what it's like to work in that organization in every job. Let's say 216 people. If you work for 1 year and we just arbitrarily break it up into teams of 3, just as an average, then to work in 6 teams is of 3 is 6 years. And then you've got another 6 years for another 6 teams, and you keep going. And so this isn't a particularly big company, right? 216 people, but it would take you 72 years to experience all of the teams in that organization. And so this is what I mean by saying that nobody experiences the organization if it's around this size, or of course organizations get much bigger than this, but this is the idea, is that you don't have an intuitive sense of what it is to be an organization, because you just don't experience, you only experience a piece of it. So that's fine, but obviously we use science to measure things that we can't see directly. So we can measure lots of things that we can't see directly, but it gets worse than that, because you can't directly measure organizations either, which sounds funny because I'm an analytics manager, so I measure all kinds of things in organizations all the time. But if you're talking from a scientific point of view, right, to measure something and test hypotheses and develop robust theories that actually really are true or objective in a meaningful sense, you need to do controlled experiments. And again, organizations are too big to do controlled experiments on. So if we look at the sciences that are used to currently try and measure organizations, they're well below that if on the y-axis you've got quality of the information and theory, they're well below that line, because you can't do controlled experiments, and that's the bar for robust theories. And if you look at organizational economics, it's similar to management science. And if you look at economics, it's to show that there's a range of things there, but they're all in the same category, that you don't have high quality theories. But if we look at the subjects that do have high quality theories because they can do controlled experiments, okay, at the top end you've got physics, and obviously everybody knows physics has high quality theories. Then you have chemistry, and we're going towards the right because the distance to what we're interested in is getting a bit less. And if you go to biology, you have a lot of the properties of physics, in the sense that you can do controlled experiments, but it's also more similar to what we're interested in, which is organizations, because biological systems are things that have to be viable, like organizations. They have to deal with risk, they have to deal with uncertainty in the environment, they have to be able to grow, they have to be able to adapt. So there's all these similarities with real organizations, right? And so in science, we have this option that we use, which is to measure something that we can measure accurately, such as by doing controlled experiments, that's a model of the thing we're interested in. And if you do this with biology, you can translate a lot of biological research as a model of human organizations, and you lose obviously a lot of the fidelity because you're not studying directly organizations. You can't, it's the dragon you can't see directly, but you're getting a good idea of what it's probably like. And so I've kind of done this by analogy. This is your organization. You know, it's a fuzzy picture that you end up with of your organization. And this isn't actually a picture of your organization. This is a picture of a black hole. But as you can see, it's quite a fuzzy picture. But people got very excited about this picture because the first time we could accurately measure something that we've never seen before. And of course, this isn't actually the black hole. This is the disk around the black hole, because the whole point is you can't measure directly a black hole, right? But we're learning something about black holes by seeing this image. And the key feature of it is that, okay, it's imprecise, right? But it's likely to be accurate. And that's because we're using scientific instruments which are accurate. And so what you lose in precision, you do gain in accuracy. And that's the difference between theories that think they can measure something. They get very precise results, but without the accuracy. So this is the difference, is that if you're precise without accuracy, you're just wrong. And what scientists want to do is gradually increase their knowledge and be less wrong, but not even wrong, which is like, you know, they don't so far out that it's not relevant. And that's what this is. It's wrong, but it's not even wrong. It's accurate, and that's what we want to do with organizations. So after I wrote this article, which is what this talk comes from, I saw this randomly in the Guardian, and it's a story about some researchers in Nottingham who are simulating black holes because the fluid dynamics of helium and fluid dynamics generally is similar to the forces that undergo black holes. So it's very interesting that this what I'm talking about, using a model as an analog of something that you can't directly measure, is fundamental to how science works. So in my opinion, this is what we should be doing if we want to learn about organizations. And yeah, I'm a bit early, but that's the talk. So it's just the introduction to the idea behind Turing Meta. And yeah, I've got 10 minutes for questions at least, hopefully. Yeah, so what I mean by that is simply that if you're inaccurate, right, you're not if you took a series of measurements that were imprecise but accurate, they would cluster, and gradually you would draw a graph and you would see them all close to the, if you're throwing darts at a dartboard, if you're imprecise but accurate, if you keep throwing darts, you gradually clump around what you're aiming for. If you're just imprecise, it just goes all over the shop and you don't even know what you're aiming at, you know. And so that's a rough analogy, right? But it's just the idea of like taking a picture of the organization. So like, say you're a psychologist and you say organizations are about people. People is the organization. There's nothing else apart from people, so that's an organization. First of all, that's not true. There are lots of parts of an organization that are not to do with people, like technology and rules and policies and documentation and the building itself and, you know, all these things. So, but if you did decide that you're going to base your whole theory of organizations around people, you might have a very precise theory and you'll say, this is exactly what you should do. And this is what people do. They come and they say, this is what we should do. And they're very precise about what they should do. But there's no error bar saying, well, do you really, this might be right. And so we're not converging like you would if you're throwing darts at a dartboard on the answer. We're just randomly shifting, you know, in terms of fashion and stuff, from one thing to another. And that's what I mean by precise without accuracy.
Similar to the thing you want to measure.
Yeah.
So in the example, you have superfluid helium similar to black hole.
Yeah.
How can you be sure that it is similar?
Yeah, so that's a great question. So what we need, right, is to have methods to sort of say, this is a good analogy. This system is a good analogy for that system. So like I gave you some rhetorical arguments, like I talked about how biological systems are more similar to to us than, say, chemical processes or physical processes. And I gave you some examples, but what we need to do is be more methodical about how good the analogy is, right? And why that should hold. Now, people will argue. So that lady, people are arguing with her that you're not going to do any new physics from studying fluid dynamics. But she thinks maybe you will if you measure it accurately and you come up with a good enough model, in her experimental setup, you might be able to learn something new about black holes. So it's an argument, right? But it's a good argument to have. It's worth having that debate. And there are ways that you can approach this. So there's a cognitive scientist called Dedra Gentner who has become an expert, like the leading expert on how analogies work, specifically scientific analogies and how they're taught. And so like examples are from thermodynamics, like an example that you would teach students about thermodynamics, and you'd use an analogy from something they know about to tell them about this thermodynamics they don't know about. And the example is if you come out of the shower and you have a small towel, you're drying yourself with a towel, but the towel's too small. At a certain point, the towel is so wet, it can't do any more drying. And that's the same thing that's happening in a room when you have something hot and it's heating up the whole room. But after a while, it gets to the same temperature as the rest of the room, so it can no longer do any useful work. And so this is the principle you can learn by analogy. And we use these analogies, to teach science. So there's a model of how those analogies work as well. So we can model that. And I'm interested in using kind of metadata and explanations of scientific theories to capture those when those analogies hold. And so there are ways to do that.
Can you prove that analogy is valid? One of the things you can't measure. Never be sure your analogy isn't completely.
No, you can measure some things about it, right? So we know some things about black holes. We can directly image some things about black holes around what's surrounding them. So you have to have some information to start with. You don't have no information, right? You have enough information to test the analogy. And then once you're happy with the analogy, you then can use the system. And what you can do is, okay, you can't confirm that you're right before, but once you make the analogy and then you set off to do certain experiments or certain observations, you can then confirm, that the analogy led you in the right direction. Whereas if you don't have the analogy, you can't.
So you can prove that black holes are similar in some ways.
Yeah.
So then you just extend that and hoping that there's.
If they come up with some physics, so they say, according to our model, it's just like a simulation. So people are using simulations all the time. It's just that this simulation is an analog in the sense also that it's a physical system that she's got as a simulation. So people use simulations all the time as models of the real thing. They're not the real thing, but sometimes they can tell you that, you should look in a certain direction or we predict this, and it's the same principle. So yeah, it's pretty useful to have simulations and models. Yeah.
To get study on organizations.
Yeah.
What is some interesting or curious insight you learned about?
Yeah, so probably the biggest thing you notice is that in biology, there is a theory called life history theory, which developed over many decades, and it's absorbed different other research into a very large body of work, analyzing the different strategies that biological organisms of all kinds and complexity need to survive, and how those strategies trade off in different ways. And one of the main things you see, the theory called RK theory, where there are this idea that there's two basic kinds of strategy for in certain ways to do with reproduction, where if you're in a very uncertain environment, you need to have a lot of options. So you have a lot of offspring, and then potentially a lot of them will survive on a good environmental situation, and potentially a lot of them will die, but some of them will still survive. And that's called an R strategy. So like salmon use an R strategy. You also have elephants and humans who use a K strategy, which is where you just have a few offspring, but you try and make sure all of them reach adulthood and maturity. And what you find in business is that there's a lot of the equivalent of a K strategy. Like we will do a big project, it has to succeed, we have to bring it to maturity reliably, but there isn't necessarily so much of the R strategy, right? There is in certain niches. So like where people are managing portfolios in innovation, investing in startups or in the insurance industry, people look at having lots of options and they just average out. But that's the most similar thing to the R strategy. What's interesting is that how in organizations, psychologically and culturally, we just focus on the K strategy all the time. But it's very unlikely that that's the best strategy all the time, because we definitely work in uncertain environments all the time. So one of the biggest take-home messages is that if you image your organization, it's very likely that you're in a very often uncertain environment, but you're still using a K strategy all the time. And this is the kind of thing, as I say, it's not very precise, but it's accurate. It's likely to be accurate. Yeah. Sorry. Yeah. I mean, to be honest, I've got lots of ideas, because once you start translating biological research, there's a lot of different things, and it's not just life history strategy. There's cutting edge research that relates to agility, for example, but it's been honed in looking at biological systems, and it's just in a more advanced state than the discussion around agility in businesses. So you can use that sometimes to give you very precise analytics about and a sense of what agility means in an organization. But a lot of it, I think, is just to do with training. It's just to do with people's, as I say, this K and R strategy is probably worth introducing to people, because that would seem to be quite an easy win to get people to think in terms of more than one strategy in terms of this dimension. Yeah.